Okay, so y'all may recall a long time ago we talked about this thing called path independence. Path independence is pretty naturally connected to the fundamental theorem of line integrals, right? So the idea, though, is that, suppose we have two curves, and we're interested in comparing line integrals over these two curves. Now, not just any two random curves, of course. You take that curve versus that curve. Now, come on, right? They're completely different. They have nothing in common with each other. We're talking about two curves that start at the same point and end at the same point. So, like that, right? These two curves that have the same boundary. Here, let me color code better than that. That have the same boundary point, same starting point, same ending point, same boundary. Right? Some vector fields have this feature of path independence, that the two line integrals will always be the same. And, again, I like to make this pitch of, oh, come on, how could a vector field possibly have this property? There's infinitely many requirements on this vector field. There's infinitely many pairs of curves that start and end at the same point, right? So how could this ever conceivably happen? And then you realize that, this is an immediate consequence, or, this feature is an immediate consequence of the fundamental theorem of line integrals for gradient fields. That's exactly what the fundamental theorem of line integral says. Well, the line integral only depends on the starting point and the ending point. It's f of b minus f of a. Right? So I'm going quickly through this because this is just a reminder of an idea that we covered long ago. Okay. All right. So what we're going to do now is consider an analogous property of vector fields relating to flux. So instead of looking at two curves with the same boundary points, we're going to think about two surfaces with the same boundary curves. Right? And so let me draw a quick picture of what that might look like. Here is a boundary curve that is the boundary of this green surface up here. And it is also the boundary of this blue surface down there. Right? Two different surfaces, but they do have the same boundary curve. We'll worry about orientations a little bit later. Okay, so is it possible, perhaps that by having this same boundary curve, might it be that somehow the flux between the flux through these two surfaces would always be the same? Is it possible that there is a vector field that is surface independent, I like to call it, by analogy to the idea of path independence? Okay. By the way, this topic's not in the book. I think it's weird. This is a really valuable idea. We're going to be able to do a lot of neat computational tricks with it. And the book kind of doesn't mention it. So anyway, this is all a little supplemental, but this is supplemental to the book, but this is definitely part of the course. Okay. All right, so let me take you over to our. I clicked the wrong button. Over to our diagram here. Remember, we had this diagram sort of bringing all these ideas together. We saw how the fundamental theorem of line integrals tells you how gradient and boundary work together as applies to curves, right? And then, etc. Right? Gauss's divergence theorem tells you about how divergence and boundary relate to each other in terms of solid regions. Flux over the boundary surface is triple integral of the divergence over the region, right? And we saw last time that Stokes' curl theorem does the exact same sort of analogous thing to surfaces and their boundary curves. Okay. All right. So what I'd like to do is start by kind of representing what we mean, where on this diagram, how would I represent on this diagram this idea of a path-independent vector field? What would that look like? And I'm going to, roughly speaking, say that a path-independent vector field is something that is kind of here. I made that too big here. Let me just do it like that. Path-independent vector fields are vector fields that have the following property, that if I were to pick two curves, again, not just any two random curves, but two curves that have the same boundary points, then the line integral is always the same. All right, and now, side note, remember, we talked about how a path, regularity issues aside, I don't want to worry about regularity, but other than that, path-independent curves that I represent like this are gradients of some function, and I can represent that with a yellow arrow there. And then we also observed, right, again, regularity issues aside, that a path-independent vector field, a vector field which is a gradient of some other vector field, has the feature that its curl is 0. Okay. All right, so this is a kind of a graphical, strategic, you might say, representation of what we know about path-independent vector fields. Path-independent vector fields. So now let's speculate irresponsibly. Well, can I just slide everything over? And does it make sense? Are there, vector fields? Let me use a different color. Are there vector fields with the property that when you look at two different surfaces with the same boundary curve, they always give you the same flux? Right? That's the question that we're asking over here on this page. We're looking at two different surfaces with the same boundary curves, and we want to know, do they always give us the same flux? Okay. So strongly analogous to the idea of path independence, and strongly analogous on the diagram. It's really just all the same ideas, but just shifted over one. Now, with that in mind, let's again speculate irresponsibly, because who knows? Hey, sometimes irresponsible speculations bear out, right? Once we make sense out of this idea of surface independence, I wonder if it might be that vector fields that are curls of something are somehow connected to it. Right? And might it be that the divergence of these vector fields ought to be 0? So we don't know those things yet. We're just kind of speculating here. But anyway, that's some things to be on the lookout for. Okay, so going back to where we were. Again, here's our picture. Now let's pay careful attention to orientations at this point. You got to at some point worry about this. When I say that this surface up here and this surface down here have the same boundary curve, we do have to worry about whether we're going around the one way or the other way. We need the orientations to work out. And so if I want them, for example, to both have this orientation on that boundary curve, what does that tell me about the orientations on those two surfaces? And we again find ourselves in this situation where these two orientations, they sort of need to be, what do we call this? These two orientations, that orientation versus this orientation, they're kind of the same in a way because they're both pointing up. But they're also kind of opposite because one of them's pointing inward, one of them's pointing outward. So are they the same? Are they opposite? What's the right way to think about this? Answer, there is no comparison. This is an apples and oranges, right? It's a total red herring question. You can't compare orientations on different surfaces. They're different surfaces. Right? So don't fall for that. Don't make the mistake of trying to decide, are these the same or are they different? They're incomparable. Everybody on board with that, first of all? Okay. So, what you do have to do, though, is pick these orientations so that they induce the correct boundary on the shared boundary curve. The correct orientation, sorry, I misspoke. The correct orientation on the shared boundary curve. And you just gotta, play the right-hand rule game twice, and, it's just gonna have to be like this, as it turns out. Okay. All right. A little bit more to say about that. We'll come back to it in a few minutes. Okay, so this is our picture, and in the same way, I'm going to be going back and forth, by the way, to the diagram a fair amount. Let me take this back over to here. Let's go back and think about path independence. How did we make this connection that there was how did we draw this connection that there was a relationship between path independence and gradients? Well, it was by an application of the fundamental theorem of line integrals. Right? The fundamental theorem of line integrals is what tells us that every gradient is path independent, because the fundamental theorem of line integrals tells us specifically that it is only this shared boundary, these 2 points, the starting point and the ending point, that these 2 curves agree on. That's all you need to know to compute that line integral if you're talking about a gradient. Yeah? Okay. Well, again, let's speculate. This kind of suggests, well, I didn't really, the highlighting here doesn't really transfer over very well. Let me just do this. So, speculating, moving this over like so. How might we, what's our clue as to how we might get an idea of how to connect surface-independent fields to curl? Well, Stokes' curl theorem, natural candidate. I mean, just by analogy. I mean, just following the pattern. This is strong suggestion that Stokes' curl theorem should give us the same suggestion, and it does. So here's the idea. Stokes' curl theorem says this and this. There's Stokes' curl theorem twice. Now these two surfaces have the same boundary curve. Right, same boundary curve. So applying Stokes' theorem to the top surface, applying Stokes' theorem to the bottom surface. Let me color code that to the top surface. Right, to the bottom surface. Applying Stokes' curl theorem to those 2 surfaces connects me to the same boundary curve, and therefore I get the same answer, and therefore these 2 fluxes are the same. Right? And this is always going to work if you have a curl field, if your vector field is a curl. This argument always works. So every curl field is surface independent. And now it's a little harder to prove, but it also goes the other way. Not only, and again, regularity issues aside, it's really not Math 212 appropriate, but not only is every curl surface independent, but every surface independent field is a curl. Okay. All right. Again, harder to prove. Okay. All right. Yes.
What is a curl? What does that mean?
Yeah. So to be a curl field, it means it's exactly what it says. It means it is a curl of some other vector field. Yeah. And this is an awkward thing to talk about because we don't know how to find the anti-curl. Right? We can talk about what it means to be a gradient. It means that you have an anti-gradient, and that feels like a safe thing to say because we know how to find anti-gradients. We know how to arbitrate that question. And sadly, we don't know how to arbitrate the question of is a vector field a curl field. Yeah, it's a great question, though. Yeah. Yes. Oh, I'm sorry, you got to follow up.
When would you use this?
Yeah, great question as well. Yeah, we'll get to that in a couple. Very natural question. Begs an answer, and it's coming. Yeah. Yes.
Going back to the title surfaces.
Yeah.
Where exactly are the surfaces and how is that bounded?
Yeah, so we've got, it's 3-dimensional, so it's hard to draw, right? But so we have kind of, think of a sort of a top piece. My hands aren't good at making weird shapes, so I'm going to make kind of a little dome on top and a dome on bottom. The way I have it drawn here is more like a peanut, right? So forgive me for not being able to do that. But you have a top surface in the form of my left hand, bottom surface in the form of my right hand. And my two hands here, like this, have the same boundary curve. Namely, where do my two hands meet? Yeah. Does that make sense? Yeah. Okay. It's just, it's hard to, artistically speaking, I could sort of do this, but then the problem is it looks like I'm filling in the solid, which I'm not. Yeah, so it's hard to draw. Okay, so there is a connection to Gauss's divergence theorem, and I am a big believer in analogies, as you all have no doubt noticed. So this next page that we're going to talk about here, please notice that I have deliberately laid this out on the page in shameless style ripoff to how I laid it out on the page, the analogous argument, way long time ago when we were talking about path independence and the fundamental theorem of line integrals, how the Green's operator and gradient are sort of connected by way of Green's theorem and by way of the fundamental theorem. So these two arguments are extremely analogous. Now, we've already seen this idea over here on the left, this argument. We've already seen an analogy of it in terms of sort of the three-dimensional version of, instead of being an R2, what if you're an R3? And Stokes' theorem. You just kind of replace this business here with Stokes' theorem, and these two arguments go through, I'm going to say, exactly the same way. Pretty much, right? Okay, so the analogy here isn't quite as direct, it's not as immediate, but it's still very strong. The big difference is that here we're shifting one dimension up. And again, we've talked about this over here. This is just this shift. One step to the right, everything shifts over in this analogy. Okay, so keep this in mind as we're going through this. In fact, I'll leave both of these pages up as we talk about this. So here we go. We're going to consider now, you can see how this is going to connect to surface independence. Here is, one surface. Here is another surface. And they have the same boundary curve. Just like over here we had one curve. Here we had another curve with the same boundary points, right? Same boundary points over here, same boundary curve. It's one dimension up. Okay? Now let's think about what's on the inside. Well, over here we had again, ignoring issues where the curves cross. That can all be handled. It's nothing to worry about. Here we have a two-dimensional region that's sort of, bounded by these two curves between them, right? Well, inside of here now, and this is another artistic sort of challenge, we have this solid that's bounded between these two surfaces. And again, all exceptions granted with, thinking about surfaces that might intersect and be all wiggly and stuff. And again, that can all be handled. It's nothing to worry about. Right, that's a distraction from the big point. So, and just for color purposes, let me trace over that again. There we go. Okay. Remember when we were talking about what is the boundary of the yellow thing over here? Boundary always goes counterclockwise, and thus C1 minus C2. And in particular, we get that minus sign. That minus sign is just intrinsic to how geometry works, right? It's not I didn't make an accidentally inappropriate choice on orientations. That minus sign is unavoidable, one way or another. Okay, same thing here, and this gets to looking at these normal vectors, right? We already discussed how this normal vector has to be oriented like that, right? This other normal vector has to be going like, I'm trying to resist saying the other way, right? But it has to be like that. And so when we say boundary, now don't forget the word boundary. Hang on a second, I'm making an artistic mistake. Here we go. Boundary always means outward. Right? So the boundary of that yellow solid just like the boundary of this two-dimensional region in there, has a minus sign in it. Right? I mean, you might say that, from the point of view of thinking about how these curves, way over on the far left, how these curves are part of the boundary of the solid region D, C2 is going the wrong way. Right? Well, as part of the boundary of this solid three-dimensional region here on the right side, S2 is oriented the wrong way. Yeah.
Why do we make N1 and N2?
Yeah, no, right, okay. We have to do that, though, because we need for their boundaries to be the same. Right? And so if you look at these, we've got this green surface, we've got this blue surface, right? And ask, well, what orientations do I have to put on these two surfaces in order for them to both have this specified orientation on the boundary curve? Right? I want the boundary, here, let me draw that on here. I want the boundary curve to be oriented this way. I need them to have the same boundary, orientation and all. Then just playing right hand rule games, those orientations have to be as we've got them drawn here. And I know my picture is getting a little muddled, so let me highlight. There's the orientation on that green surface. And there's the necessary orientation on the blue surface. So you really kind of have to do it that way. Yeah. Okay. Yep.
Doesn't the f.ds give you the surface? Not give you the surface integral, gives you the flux.
I'm sorry. Where are you? Are you a little ahead of me? It looks like.
No.
No.
When you say Gauss' divergence theorem is equal to S1 f.ds.
Yeah.
Because you're trying to draw like a similarity with Green's theorem.
Yeah.
But doesn't the Green's theorem one actually give you the line integral, whereas that one, does that give you the surface integral, or just gives you the flux?
So you're just a little ahead of me, but that's the very next thing that we're going to talk about. So I'm going to delay you for about 10 seconds here. But first of all, I'm going to pause and make sure, is everybody comfortable with the comparison of these, the setup here of what's the boundary of what and which way are the orientations going? Does everybody see how this is all everything connects there? Is everybody good? Okay. All right. Okay. So let's talk about then. How does Green's theorem apply over here? We've got this region. Well, Green's theorem says that. Green's theorem is a statement about how a double integral over the interior relates to a line integral around the boundary. And don't forget the boundary has these two pieces, C1 and C2, and there's a minus sign and et cetera, right? Is that cool? Okay, so the analogy, let's apply Gauss's divergence theorem to this, and I'm in pencil mode, let's apply Gauss's divergence theorem to this solid. Claim Gauss's divergence theorem tells us this, there's a triple integral of divergence, and it's equal to boundary flux. And boundary, again, the word boundary means outward oriented, right, and with just like that boundary has a minus sign in it, this boundary has a minus sign in it, and so we get this. Did that answer your question?
Yeah.
Okay, cool. Okay, so again, this is shameless ripoff. We're taking all the ideas that we applied before to path independence and the fundamental theorem of line integrals and Green's theorem, and we're just going to kind of shift it on over. Okay, so now the analogy continues. What can we do with this? Well, let's speculate what would happen if the divergence were zero. Let's just play the game, and by the way, why are we asking the question? Why is it, what if the divergence were zero? Well, because our diagram is like telegraphing to us, hey, this may be connected to the possibility that divergence is equal to zero. So we're exploring a strongly suggested possibility here. Right? Okay, so what if divergence is equal to zero? Well, if the divergence is zero, that integrand is zero. That means the triple integral is zero. That means this difference is equal to zero. That means that these two line integrals are equal to each other. Why did I say line integrals? Surface integrals are equal to each other. Right? I must have been looking at the other page. Well, if two fluxes are always equal whenever the two surfaces have the same boundary curve, that is the very definition of surface independence, and we saw on the previous page that means it's a curl. Yeah. And so now it seems like a reasonable thing to go the other way. What if we have a curl? A vector field that is a curl of something. Well, if it's a curl of something, we already know it's surface independent. Surface independence means that these two integrals are equal to each other, which means that this difference is 0, which means that this triple integral is 0. Okay, well, hold up. How could a triple integral be 0 over every possible solid, no matter what solid you pick? The triple integral is always 0. Well, that means that integrand has got to be 0. So the divergence is 0. Okay, so we have this highly analogous result in the same way that Green's operator being 0 is a tip-off to being a gradient and therefore path independent, and vice versa. Divergence being 0 is our tip-off to a vector field being a curl and therefore surface independent. Everybody on board? Okay. I get really excited about the strengths of these analogies between ideas applied in one context versus another. And again, let's go back over here to the diagram. Now you can see everything fits, right? In the same way that path independent fields that have this property, by virtue of this theorem, give us the fact of being gradients, which by clever argument tells us that the curl is 0. Well, by analogy, we just went through all the details. Surface independent fields, by virtue of Stokes' theorem, are all curls, and by an application of divergence theorem, all have divergence equal to 0. And I think I saw a hand shoot up there for a second, but I wasn't. Yeah, okay, yeah.
So if it's a curl and the divergence is 0, so that motivates our lifetime theorems?
Yeah, absolutely. So that's a very reasonable way to take this, is that this argument that I've given here for surface independence connects to being a curl, surface independence connects to divergence being 0, motivates these two theorems down here. Yeah, absolutely. Exactly. So we already knew that these were true. Now we have a good motivation for why they should be true. Okay. Alrighty. So now, why do we care about any of this, aside from the Nito factor? And it's a very powerful computational tool. A real quick flashback, though. Right? This idea of surface independence is in comparison to path independence, and we kind of agreed that path independence wasn't. I mean, look, conceptually, sure, connection between different ideas has applications in lots of ways. Physics, cool things you can do in physics with this concept of path independence. But as a computational tool, if you can use path independence, it's a gradient. You can just compute the anti-gradient and use the fundamental theorem of line integrals. So who cares in some sense? From a computational point of view, this is a nice hammer, but we already owned a hammer, right? So it doesn't allow us to do anything that we couldn't already do before in broad strokes. Okay, so why doesn't that same thing apply here? And let's just kind of carry it through and think it through. Well, if it's surface independent, well, that means it's a curl. Can't I just compute the anti-curl? Oh, wait, no, I can't. Right? We don't know how to compute anti-curls. So what this is this is not a hammer, and by the way, we already previously owned a nice hammer. This is a screwdriver, and we did not previously own a screwdriver. Big win. Everybody see the point? Okay. All right. So let me show you how you can really capitalize on this in a very nice way. Let's look at this question here. Here's a vector field, and here is a surface. So we've got, by the way, let's take a moment to look at this surface. This surface is a elliptical paraboloid. I hope everybody remembers all that business from chapter 12. And you can see this is a upside down paraboloid that's been stretched by different amounts in the x and y direction. So elliptical paraboloid. Wait, no, it's not the whole elliptical paraboloid, just the part that's above the xy plane. So this is an upside down bowl. Kind of weird, oblong, upside down bowl, right? With an orientation given. Fine, okay. So right. So how am I going to compute the flux of this vector field through that surface? It's a problem. Now I made the following gripe previously. I want to do it again just to show you, because the following is a landmine. It's a nasty landmine, and several students every year step on this landmine, and I'm trying to get that number as low as possible, right? So please don't make the following mistake. A lot of students will do the following, and they'll say, hey, well, I'm going to compute the divergence of this thing, and the divergence, oh my gosh, the divergence is 0. Well, then, look, flux is a triple integral of divergence. What's called G. Flux is a triple integral of divergence, and therefore a triple integral of 0, and therefore 0. Check. Box. Smiley face. Right? I see this on tests all the time. And it's a heartbreak for me, because I can't give any points for this. This is worth nothing. I might be able to give 2 for correctly computing the divergence. Everything after that is nonsense. It's absolute nonsense. Because the divergence theorem that you're quoting here, the student that writes this down, okay, is saying that flux is a triple integral of divergence. Somehow I missed one of my little things there. Flux is a triple integral of divergence, and no, it isn't. Flux through a boundary surface is a triple integral of divergence. Through the anti-boundary, through the solid that surface was the boundary of. This surface is not a boundary, right? This surface is an upside down bowl. The surface looks like this surface here. I think I have a picture of it here. Here it is. The surface is just this. It's not a boundary. Yes. It is open on the bottom, absolutely. And now a lot of students like to, I think a lot of students are sort of deluded by the picture, right? So we draw sort of the boundary down here to denote that that's where the paraboloid stops, right? And then psychologically that tends to make students think that, well, somehow then it must be filled in here, but it isn't. Right? This, if you look at the definition here, it says we're looking at part of the paraboloid. This is a subset of the paraboloid, right? And that is not part of the paraboloid. Does that make sense? Very tempting, though, right? Give me 2 seconds. So the surface that we're looking at here is just that one, just the sort of this part. Yeah.
So if the question said like the bounded between z equals 0 and
so you got to think carefully about the phrasing, and one way or another what you're going to end up with is rephrasing the question as, suppose your surface is the boundary of this solid defined in a certain way, right? And right there in the phrasing of the question is, the surface is the boundary of a given solid. So that dramatically changes the question. Then this, what I have in purple here, would be quite right. And sometimes questions are easy, and yeah, absolutely, yeah. But very importantly, that's not what this says. Yeah. Okay, so everybody be real careful about this. Interpret the question strictly carefully. Otherwise, what you write down doesn't make any sense. Everybody on board? Does everybody see the problem? This surface is just not a boundary. So right off the bat, what I have highlighted in yellow here, wrong.
bit confused, like on the, like, I'm like,
The phrasing of the question and what is the actual thing?
yeah, will we be able to ask?
You can ask, but I'm going to be limited on how I can clarify. I mean, so in other words, I can only help you if there's an ambiguity on that, right? So the way this is phrased, I think this phrasing is actually pretty clear. It says S is the part of this paraboloid with z greater than or equal to 0. And so the paraboloid right there tells you it's a surface. There's no ambiguity there, right? One thing you might want to do is maybe look through my old exams and see a bunch of examples of, descriptions of surface, verbal descriptions of surfaces, and then, think to yourself, try to come up with the idea of what does this surface look like, and then check the answer and see if you got it right, that kind of thing. Yeah. But if there's an ambiguity in the statement of the question, then yeah, absolutely. By the way, I have a history of inadvertently forgetting to indicate an orientation. So if that happens, and I'm getting better at being careful about that, right? But if I should forget to indicate what the orientation is, you absolutely should ask. Yeah, right. Okay, right. So don't make this mistake. Don't step on this landmine. Again, that's worth. I think for correctly computing the divergence, I might give 2. So that's a 2 out of 20. Yeah. There's nothing correct other than a triviality. Nasty little landmine. Okay, so let's talk about the correct solution to the problem. The divergence is 0. That is true, and it is relevant, just not in that way that we were talking about. The fact that the divergence is equal to 0 tells you Well, it tells you a couple things. One, I suppose, if you wanted, you could say, hey, that tells me that this is a curl field, and I suppose if I could find the anti-curl, then I could rewrite this flux as a line integral using Stokes' curl theorem. Sadly, we don't know how to find an anti-curl, so that's not a viable option, right? But the other thing that it tells you, the divergence being 0, is that this is a surface-independent vector field. That means you can take not the surface you were given, but take any other surface with the same boundary curve and just change your surface. And you're going to get the same value of the flux. Okay. All right. So going back to it. So let's look at our surface. Again, we have this elliptical paraboloid here, oriented upward. So there's our orientation. The boundary, let's think about what the boundary of this upside down bowl is. Well, the boundary is the lip of the bowl, if you will. Let's think about the orientation on the boundary, right? This is important. You're going to be off by a minus sign otherwise, and it's conceptually a big point. Thumb, fingers, swirl. Boundary curve is oriented that way. All right, so I have now the right to pick any other surface that I want. Right? By virtue of surface independence, I can pick any other surface that I want as long as it has the same boundary curve. And just say, phooey on this green surface I was given. I don't like it. It's all curvy and stuff. I don't like stuff that's curvy. Right? So I'm going to pick the easiest surface I can think of. Right now, don't make your life unnecessarily difficult. You could pick that upside down paraboloid, right? Or you could be, how about, this glove, right? Imagine a glove, right? That's an option. It's perfectly legal. Don't do that to yourself, right? So obviously, pick the convenient one, right? This surface in the XY plane has the right boundary, and now you got to worry about orientations, right? So think it through. Does it this way or is it that way? Fingers and swirls and side swipes, and not hard to persuade yourself that the orientation's got to go up. Okay, so surface independence tells us that instead of looking on the green surface, I can instead look at the yellow surface. Right? Thank you, surface independence. And turns out, I mean, the integral over this yellow surface is kind of convenient. The normal vector is really easy to write down, right? This normal vector here is just 0, 0, 1. So dotting this with our normal vector of 0, 0, 1 gives me just xy. I have an integral of xy then over this new surface, and it's highly susceptible to a convenient symmetry argument, and the integral is 0. Symmetry through the x-axis or y-axis, take your pick. Everybody on board? Oh, but hey, here's another thing that keep a lookout for. Another thing that we could have capitalized on. Had this expression in here had some z's in it, maybe, right? I mean, look up at the formula here. There could have been z's in the formula for this. There didn't happen to be, but if there were z's in there, any z's, by virtue of our clever choice of having made our surface in the xy plane, any z's would be 0. Right? So we didn't need that point here, but who knows? Might be useful. Okay. Really, really clever idea. Very powerful tool. I'm a big believer in it. Again, due to the lack of good alternatives. Okay, some quick discussion of physics. I'm not going to spend a huge amount of time on this, but I think some of y'all may have had an E&M class already, either here at Duke or possibly in a high school physics class. And if you haven't, don't worry about it. But here's a reality of the physical, the way E&M works. If you have a current in a wire, current just means there's a bunch of charged particles that are moving through the wire. It's like a flow of a kind of a fluid through the wire, right? Current in the wire creates what's called a magnetic field by this wrapping around kind of thing. So the current going that way makes a magnetic field right, okay. It's easy to get that backwards. Makes a magnetic field that kind of wraps around like that. Yep.
Should we go the other way?
Well, let's think this through. So right hand, right? So if the current's going this way, then it's going like that. So I think it should be going around like this. So I was trying to draw. Now how we draw that is awkward, right? So I was trying to draw the field that's sort of on the near side of that line, and then over here it's on the far side. It's just artistically hard to draw, right? And there's so many little inadvertent Escher, coincidences. It's hard. You know what I mean? But you see what I'm talking about, though? Yeah. Right. Okay. So the point is, you get this magnetic field represents this thing called a magnetic field, and what you do with magnetic fields, not our problem, right? But there's rules about how if a charged particle is moving through a magnetic field and that creates resulting forces. We're not interested in that in Math 212. That's for engineering and physics classes. Okay, so something analogous happens in the analogous situation of instead of having the current, keep in mind current is just a flow of charged particles, instead of having it confined to a wire, what if you have this flow just kind of loosely in space, like a fluid of charged particles just flowing, like this through space? Well, that creates a magnetic field as well. And not surprisingly, the magnetic field has some common features. Right, it's kind of wrapping around in a way, and again, right-hand rule. So, unsurprisingly, I'm going to say, let's think about, what might this have to do with curl? Keep in mind that curl is kind of a way of measuring the extent to which a vector field is kind of flowing around. Well, look, this green magnetic field here is kind of flowing around that current field. Right? The current field here, let me color code. the field representing the flow of charged particles is representing how the green magnetic field is wrapping around. And so the unsurprising result, with that in mind, is that the curl of the magnetic field is the current field, J. And there's a constant in there. The constant's, again, not our problem. That's for physicists and engineers. But some constant, right, as far as we care, times the flow field. Okay, so this is a connection to physics. It's a very important connection to physics. I mean, magnetic fields are important. Currents are very important. And so this is this is another one of Maxwell's laws. And by the way, we're going to skip this business here about physical construction of an anticurl. I really enjoy this little point, but we don't have time for it. It's not in the book. It's not part of the course. I just think it's fun, right? So if you want to talk about that, please, but come talk to me in office hours, but you're not responsible for it. But let's look at Maxwell's equations real quick, and we're gonna be pretty quick with this. Here's the one we just wrote down. The curl of the magnetic field is proportional to the current field. There's another kind of analogous fact that we just can't. I mean, again, this is not a physics class, so I'm not going to be able to give you any motivation for this, but the curl of the electric field is the time rate of change of the magnetic field. And this is a weird one because you can see time rate of change is immediately suggesting that this is not a steady state situation. This suggests that somehow your magnetic field is changing, so stuff's moving, right? It's a little weirder. Nevertheless, these are two of Maxwell's equations. These are what I like to call Maxwell's equations numbers 3 and 4. Remember we talked about 1 and 2? That 1 and 2 had to do with divergence. 3 and 4 have to do with curl of the E and B fields, just like 1 and 2 were about the E and B fields. Okay, so we call these the differential versions of these theorems by strong analogy with what we did with the first two. Here they are again. Yeah, just rewriting those. Now let's take a surface integral of both sides of this equation. Don't forget Stokes' theorem. Stokes' theorem says that a flux of a curl is a line integral. Not hard to persuade yourself, and I'm going to zoom in a little bit. Well, in fact, this is just a definition. Here we have the very definition of the flux of the magnetic field. And down here we have what you could very reasonably call the flux of the J field, but don't forget, the J field is a flow of a fluid. An actual J is representing the flow of charged particles, thought of as a fluid, right? So flux of a vector field representing a flow of a fluid. That flux says literally how much of the stuff of that fluid is passing through the surface, and how much of the stuff, the stuff is charged particles. How much charged particles is flowing through is the definition of current. And if you had some E and M, you might recall that. If you haven't had E and M, don't worry about it. You can just take that as a given. Anyway, the punchline is then that altogether, from this down to this, and likewise on the other side, we have two new versions of these theorems. And so let me try to get them all on this page at the same time here. So the differential version of the theorem are, again, stated in terms of derivatives. They're about curls, right? Curls are about circulation density oriented. Okay, but circulation density, these are about circulations. So circulations versus circulation densities, you can see in terms of how you would interpret these equations, they're really, really analogous. They're really, really similar. So just like we did in the previous case, instead of calling these separate equations, we call them different versions of the same equations. So again, differential versions, integral versions. You're going to see this all the time in physics classes, E&M classes. They'll routinely refer to this as one equation, two different forms of one equation, and likewise for the other one. And so we're out of time. So good stopping point. See y'all on Friday. Oh, I have homeworks to return. If you'll hang out for a minute. Let me think now. Something else. And I owe you an email about what homework is due at the end of this week. I'll send out that email as soon as I get back to my office and remember together. And if I don't send the email by 5 p.m., please remind me. Last quick announcement. Don't forget we have a test next week. Right? Next Wednesday, right, on the calendar. The cutoff date for fair game material is Friday. So however much material we finish by Friday, that's what will be fair game for the exam. And I feel very good about the idea that we will finish the rest of chapter 15. But we won't now. Of course, don't forget we have skipped all the optimization stuff. Right, so we do still have to go back to chapter 13, and we have 3 sections to cover back there, one of which is super quick. So we have 2 days worth of material still to cover. So we're still tight on time in the course, but we are going to definitely. I feel very confident we'll finish chapter 15 before the exam. Okay, see y'all later. Oh, and stick around for the homework.